Welcome to this video. This is the third video in what's becoming a veritable series of videos on Leonhard Euler's Introduction to the Analysis of Infinities. I was only originally planning to do two videos, but after thinking things through, I thought, what the hell, why not make a third video as well? So this video will continue what I've already started, and therefore we're going to take a look at chapters 6 and 7. This video is relatively comprehensive in terms of translations, but there are a few sections for which I don't include translations in this video, and this is usually because I couldn't really get to a translation that I was satisfied with, or even that I was prepared to present to the world. As I previously mentioned, these videos can take some considerable time to put together, and it gets to a point where I've spent so much time on putting the content of a video together that I often have to go against my sometimes almost paralyzing perfectionist tendencies and just put the video out as it is. So for these outstanding sections that don't have translations, if need be, then I'll try to give an idea of what's going on, but without providing any on-screen translation. Even the sections that I have provided translations for may not be full translations and may be missing a sentence here and there. Maybe I'll try to improve my translations in the future, who knows. So in these two chapters, Euler presents things a bit differently to what we've seen in previous chapters. In previous chapters, it's typically been that each section starts with the statement of some result or definition, and then Euler goes on to provide an explanation, a justification, or some kind of elaboration. Here, however, we find that, with possibly a couple of exceptions, the results of each section are less well signposted and are kind of embedded within the text of the section, meaning the results have to be almost extracted from the text of that particular section by the reader. So I'll try to give some sort of summary for most, but not necessarily all sections from the chapters covered in this video. Some of the summaries may be quite short, simply because, well, there's not really much to summarize, but other sections may have a more in-depth explanation of the contents. I'll also be including various quotes in this video from Maurice Klein's book, Mathematics: A Loss of Certainty. This is a book that I happened to read recently, and which had some interesting passages which helps to clarify some of the sections of the chapters covered in this video and gave me some ideas about possible ways to interpret other sections. So let's make a start. Chapter 6, on exponential and logarithmic quantities. Section 96 gives Euler's definition of exponential quantity by giving examples of some of the different forms of expressions that may be considered exponential. These quantities are, quote, not accounted for by algebraic functions, the kinds of functions that were introduced in chapter 1 and were the focus of the first 5 chapters. Moreover, exponential quantities are those powers the exponent of which is itself a variable quantity, rather than the constant powers that characterize algebraic functions. In section 97, Euler builds up step by step the values of exponential functions, starting with positive integral powers, followed by zero and then negative powers, fractional powers, and briefly touching on irrational powers. Euler asserts that a to the power of the square root of 7 will have a determinate value, but he doesn't justify his assertion in any substantial way, nor does he give any indication about how to calculate the value of such an expression. It seems to follow from this that he is sure that the square root of 7 has a determinate or unique fixed value. This, even though the notion of irrational number was still quite vague in Euler's time. The nature of irrational numbers was not at all agreed upon, and it wasn't even certain whether irrational numbers were actually numbers or whether they should be considered numbers. I just want to spend some time discussing how irrational numbers and other types of numbers may have been viewed by Euler and some authors a couple of centuries either side of Euler. The positive integers and positive fractions were considered as existing in a very definite sense and didn't present any conceptual difficulties. However, irrational numbers were a different matter. Some mathematicians around the time of Euler rejected irrationals while others accepted them. Here are some quotes from Klein's book, Mathematics: The Loss of Certainty, which give some idea of the kinds of attitudes that various mathematicians held around Euler's time on the subject of irrational numbers. Calculations with irrationals were carried on freely, but the problem of whether irrationals were really numbers troubled some of the very same people who worked with them. Klein talks about, I'm not sure how to pronounce this, Michael Stifel or Stifel, I'm going to go with Stifel, and some comments that Stifel makes in his 1544 work, Arithmetica Integra, which I'm not personally familiar with, but he quotes Stifel as writing, "Since improving geometrical figures, when rational numbers fail us, irrational numbers take their place and prove exactly those things which rational numbers could not prove. We are moved and compelled to assert that they truly are numbers, compelled, that is, by the results which follow from their use." And Stifel goes on further to say, on the other hand, other considerations compel us to deny that irrational numbers are numbers at all. To wit, when we seek to subject them to numeration, decimal form, we find that they flee away perpetually, so that not one of them can be apprehended precisely in itself. Now that cannot be called a true number, which is of such a nature that it lacks precision. Therefore, just as an infinite number is not a number, so an irrational number is not a true number, but lies hidden in a kind of cloud of infinity. Klein then says that Stifel added that real numbers are either whole numbers or fractions, and obviously irrationals are neither, and so are not real numbers. Klein also says, Pascal and Barrow said that irrational numbers are mere symbols which have no existence independent of continuous geometrical magnitude. And Stevin recognised irrationals as numbers, and John Wallis, in his Algebra 1685, also accepted irrationals as numbers in the full sense. What's perhaps more surprising are the reactions towards negative numbers. Here's another interesting quote from Klein. Let us examine the predicament in the early 19th century. We can pass quickly over the few objections that were still made to the use of irrational numbers. These could be thought of as points on a line. Intuitively, they were not much more difficult to accept than whole numbers or fractions, and they obeyed the same laws as whole numbers and fractions. As to their utility, there could be no question. Hence, though there was no logical basis for irrational numbers, they were accepted. The troublesome and intuitively unacceptable elements were the negative numbers and the complex numbers. It's sometimes quite surprising how differently mathematicians viewed certain types of numbers in previous centuries compared to how modern mathematicians would tend to view the same types of numbers. We often take for granted concepts such as irrational numbers and negative numbers. At certain times throughout history, there were very different views. In the same period of time, some mathematicians may deny the existence of certain numbers, while others asserted the existence of the same numbers. How a particular mathematician thought about, say, negative or irrational numbers, and of course imaginary numbers, wasn't always consistent, and certainly from a modern perspective, the various views expressed can seem very confused and muddled. The following is a quote again from Klein, which shows that although Euler was an authority in mathematics, his views were sometimes quite confused looking at things from a modern perspective, and he certainly didn't have the final word on the matter. Klein says, Euler took up the expansion 1 over 1 plus x squared, which is equal to 1 plus x to the power of minus 2, which equals 1 minus 2x plus 3x squared minus 4x cubed plus and so on. For x equals minus 1, he obtained infinity equals 1 plus 2 plus 3 plus 4 plus and so on. And this sum seemed reasonable. However, Euler then considered the series for 1 over 1 minus x, namely 1 over 1 minus x equals 1 plus x squared plus x cubed plus and so on. And let x equals 2. Then minus 1 equals 1 plus 2 plus 4 plus 8 plus and so on. Since the sum of the right-hand side of this series should exceed the sum of the preceding one, Euler concluded that minus 1 is larger than infinity. Some of Euler's contemporaries argued that negative numbers larger than infinity are different from those less than 0. Euler objected and argued that infinity separates positive and negative numbers just as 0 does. And finally, before moving on to the next section, it seems that Euler does not consider the possibility of transcendental powers of the number a. Section 98 gives some basic properties of exponential functions. As in certain sections of previous chapters, in some of these sections, including this section, section 99, We see Euler freely using the symbols plus infinity and minus infinity as if they represented, say, a finite real number. This doesn't mean that Euler arrives at invalid conclusions, but simply that the reasoning that he uses to arrive at these results lacks rigour to a certain degree. And we also see Euler discuss the properties of the exponential function a to the power of z when a equals 0. And in this case he claims, quite rightly, that 0 to the power of z equals 0 for all positive z, but he also asserts effectively that 0 to the power of 0 equals 1. The symbol 0 to the power of 0 is sometimes considered undefined, but when it is assigned a value, admittedly, it is often assigned the value 1. We also see that for negative values of z, Euler says that 0 to the power of z will be an infinitely large value. In modern mathematics, the symbol 1 over 0 is often, though not necessarily always, considered undefined. It's possible that by saying that 0 to the power of z will be an infinitely large value, that this is Euler's way of saying that it is undefined, but using the terminology available to him at the time. A quote from Klein gives some insight into the way that infinity was viewed by Euler. The Greeks generally regarded infinity as an inadmissible concept. It's something boundless and indeterminate. Later discussions were sometimes befuddled because many mathematicians spoke of infinity as a number, but never clarified the concept or established its properties. Thus Euler, in his Algebra 1770, said that 1 over 0 is infinite, though he didn't define infinite and merely represented it by the symbol infinity. And then said without question 2 over 0 is twice as large as 1 over 0. More confusion was created by the use of the symbol infinity in situations such as the limit, as n approaches infinity, of 1 over n is 0. Here the symbol infinity means merely that n can take larger and larger values, and can be taken so large but finite as to make the difference between 0 and 1 over n as small as one pleases. The actual infinite is not involved. No reference is made anywhere of the graphs of any of these functions, but we also see Euler effectively say that the function 0 to the power of z is discontinuous, again without him actually using the word discontinuous. Euler didn't assume in his original description of functions in chapter 1 that functions were continuous, though he does effectively use the fact that integral functions are continuous to prove the result of section 33. Section 101 indicates some properties or laws of indices. Section 102 defines the notion of logarithm and what is meant by the term base in relation to logarithms. Section 103 shows some basic properties or laws of logarithms. And note that, unlike the modern notation for logarithms, the base of the logarithm is not explicitly symbolized in the notation used by Euler for logarithms. The base of the logarithm would presumably therefore have to be determined from the context. Section 104 gives further properties of logarithms. In some cases, a few examples are given to establish a pattern from which the general law is to be presumably extracted by the reader. Euler doesn't express all of his general results explicitly in a general form. Section 105 seems to be saying that the rules deduced in sections 103 and 104 show that the logarithm can only be a rational number in the case where the number is in fact a rational power of the base. He then goes on to establish the transcendental nature of logarithms, that is, that the logarithms of rational and irrational numbers will be transcendental numbers. I think I may have mentioned this in a previous video, but I'll just note again here that when Euler refers to irrational numbers, he seems to really have in mind that what we would now typically refer to as algebraic irrational numbers. Thus Euler considers transcendental numbers as forming a separate category of numbers from irrational numbers. In modern mathematics, the category irrational number includes both algebraic irrationals and transcendental irrationals. Not so in Euler, as we can see when he writes that logarithms of numbers which are not powers of the base a can be expressed neither rationally nor irrationally. That is, they can only be expressed as a transcendental number. This also seems to suggest that by power of the base he's considering only rational or irrational powers, irrational in Euler's sense that is, and that transcendental numbers are not considered as capable of being powers of the base. And a minor point regarding section 105 that had me scratching my head for a while and makes me doubt my understanding of the section somewhat is that Euler appears to express the genitive singular of basis using two different forms, baseos and basis. I don't know if this is my misunderstanding of the text, but I just thought it was strange that he used two different forms. And unless I've overlooked it, I also don't recall, at least not offhand, Euler using the form baseos anywhere else. My translation for section 106 is incomplete, with the last few sentences left untranslated for the time being. However, this section is indicating a practical way to obtain the approximate values of logarithms. This section is followed up by an example illustrating how this method works, which I've left untranslated in this video. In section 107, as we see, the logarithm of n with respect to the base a is p, and with respect to the base b is q. Euler then shows that the ratio p over q must be constant, so even though p and q will of course vary as n varies, the ratio p over q remains the same. That is, if m is another number different to n, and the logarithms of m to bases a and b are p primed and q primed respectively, then p primed over q primed is equal to p over q. This then implies that unknown logarithms of numbers to any base can be systematically computed from known logarithms to a different base. So then we have the result of section 108, which is, hence it follows that the logarithms of two numbers in whichever system maintain the same ratio. Section 109 takes some of the results of section 104 to show that it's only necessary to know the values of logarithms of prime numbers, for then the logarithms of any positive integers can be found simply by splitting the integer down into its prime factors and forming the sum of all the individual prime factors. In section 111, Euler shows how an equation of the form a to the power of x equals b can be solved for x by means of the properties of logarithms established in this chapter. My translation for section 112 is also incomplete. The first few lines are omitted. Here we see the notions of characteristic and mantissa defined. And for section 113, I've not been able to translate the final sentence of this section, since I've not been able to determine what is meant by the word manductionibus. Any help here would be gratefully received. But the last part of section 113 seems a bit cryptic, but I'll try to explain what I think it means. So let's have a look at the following logarithms, where the base of the logarithms is 10. The logarithm of 56 is equal to 1.748188027, where the characteristic of this logarithm is 1. The logarithm of 5.6 is 0.748188027, where the characteristic is 0. The mantissae of both of these logarithms are equal, but now see what happens when we take the logarithm of 0.56. The logarithm of 0.56 is equal to minus 0.2518111973. Here the characteristic is, as far as I understand things, minus 1. The characteristic seems to be equal to, though not necessarily defined to be, the largest integer that is smaller than or equal to the value of the logarithm, and not just the number before the decimal point. Thus, for a positive valued logarithm, the characteristic is identical with the number before the decimal point, but for negative valued logarithms, the characteristic is usually not identical with the number immediately preceding the decimal point. But what we also see when we take the logarithm of 0.56 and consequently obtain a negative valued logarithm, since 0.56 is less than unity, the mantissa appears to be different. So let's continue taking logarithms. The logarithm of 0.056 is equal to minus 1.2518111973. The characteristic of this logarithm is minus 2. The mantissa is still different from the first two, but is the same as the third logarithm that we found. And I think what Euler is getting at in this section, and this is probably because logarithm tables were being used, is that if we want to find the number whose logarithm is minus 1.2518111973, for example, then we'll have problems if we use the mantissa whose digits are 2518111973. Using logarithm tables, at least so that what I do resembles what Euler would have had to do, with the mantissa with digits 2518111973 gives a number whose initial digits are 177. Since the logarithm minus 1.2518111973 has a characteristic of minus 2, then the number whose logarithm this is should be 0.0177. But it isn't, since the logarithm of 0.0177 is equal to minus 1.75202. That is, Euler's method hasn't returned the correct value, and this is because the mantissa that we need to be using is in fact the one with digits 748188027. So instead of writing the logarithm of 0.56 is equal to minus 0.2518111973, and the logarithm of 0.056 is equal to minus 1.2518111973, we are instead to write the logarithm of 0.56 is equal to 9.7481888027 minus 10, and the logarithm of 0.056 is equal to 8.7481888027 minus 10. And this gives us the correct mantissae to use to find the digits of the numbers we're after, and then we just have to note the characteristic to determine the specific numbers. In the description to this video is a link to the logarithm tables that I used to do the calculations in this video. There are some sections in these logarithm tables which also explain what Euler is talking about, and probably much more clearly than I've done here. Of course, there's no real reason nowadays to use logarithm tables when calculators are available to use, and will do the job much more quickly and efficiently. Okay, so that's the last section of this chapter. Let's move on to the next chapter. Chapter 7, on the expansion by series of exponential quantities and logarithms. In this section we see Euler use the letter I to stand for an infinitely great number, for example in section 115. Note that I here does not denote the square root of minus 1. Indeed, Euler uses the literal symbol, the square root of minus 1, to denote the square root of minus 1, as we saw in, for example, section 31, which I covered in the first video. There are some concepts that Euler uses in this chapter, such as infinitely great quantities and infinitely small quantities, which, from a modern perspective, are quite unusual, and I've not been able to determine to my complete satisfaction exactly what Euler had in mind when he uses these phrases. I have, however, included some quotes from Klein, which may help to shed some light on things, even if complete clarification is not forthcoming. In section 114, Euler appears to be making use of infinitesimals, and he assumes that they satisfy the same kinds of relations that finite numbers satisfy, such as equality and inequality. He also assumes that it's possible to find a k which establishes the equality psi equals k omega. Euler seems to suggest in section 114 that infinitely small numbers are a different type of quantity to, say, real numbers. Quote, from the preceding chapter, it's agreed that unless psi be an infinitely small number, that omega cannot be of that kind. However, in Klein, we read that he, Euler, denied Leibniz's concepts of an infinitesimal, that is, a quantity which is less than any assignable magnitude and yet not zero. Klein goes on further to say that Euler, in his 1755 Principles of Differential Calculus, argued that there is no doubt that every quantity can be diminished to such an extent that it vanishes completely and disappears. But an infinitely small quantity is nothing other than a vanishing quantity, and therefore the thing itself equals zero. It's in harmony also with that definition of the infinitely small things, by which the things are said to be less than each assignable quantity. It certainly would not be able not to be nothing, for unless it is equal to zero, an equal quantity can be assigned to itself, which is contrary to the hypothesis. We can see from this that certain concepts were not completely agreed upon by various mathematicians, Many differing and sometimes incompatible opinions were maintained. Therefore, it has to be taken into consideration that when one author uses a particular term, then it doesn't mean that another author who uses the same term is using it in the same sense, and it's important to try to understand how a given author is using a particular term, since understanding this may help to better understand their arguments, even if the arguments are ultimately flawed. It may be that certain authors appear to contradict themselves and each other from time to time, and it may also be the case that certain authors were not themselves even really sure what they thought about certain concepts, and were able to make only vague statements. In section 115, Euler used the symbol I to represent an infinitely great number. In earlier sections, we saw Euler use the familiar infinity symbol to represent infinity, for example in section 34. And so there does seem to be some difference in the way that infinity and I are to be interpreted. My thoughts were that he used I to be some kind of variable that ranges only over integers and can be made as large as one wishes, whereas infinity ranges over all possible real numbers, whatever Euler understood by real numbers, and again can be made as large as one wishes. I'm not too sure about this interpretation because arguably there's nothing in the way that Euler used the symbol I that would necessitate it only ranging over integers, although having it range over integers would do everything that Euler needs it to do. Nevertheless, in section 115, it seems to me that Euler is taking I to be some kind of variable ranging over positive integers, initially in order to arrive at the expansion of 1 plus k omega to the power of I, and as we'll see in the next section, that is section 116, Euler effectively allows I to become apparently literally infinite, at least that's what it seems to me. This is very close, in my opinion, to the modern conception of limits. However, Euler does take some steps without justification that from a modern perspective would really require a bit more careful consideration. Therefore, as we see in section 116, Euler takes the expansion for a to the power of z, found in section 115, and allows I to be literally infinite, and derives an expression in the form of an infinite series for a to the power of z. The result here is not wrong, but of course, generally speaking, more care would be required to make this transition from an arbitrarily large, though still finite I, to an infinite I. And this is just one example of where Euler was on the right lines with what he was doing, but the ideas and techniques that he was applying eventually had to be tightened up. Speaking of some of the views of a number of 18th century mathematicians, Klein says in his book, the distinction between a very large number and an infinite number was hardly made. It seemed clear that a theorem which held for any finite n must hold for n infinite. Here's another quote from Klein's book, and although it doesn't specifically relate to Euler, it illustrates how certain concepts were considered around Euler's time, at least by some mathematicians. Klein describes a principle called the law of continuity, which Leibniz explains as follows. If a variable at all stages enjoys a certain property, its limit will enjoy the same property. Or alternatively, in any supposed transition, ending in any terminus, it's permissible to institute a general reasoning in which the final terminus may also be included. Of course, this principle is not considered valid in modern mathematics, and there's nothing in Euler's introduction that specifically suggests that he had this principle in mind, but there are instances, as we've seen, where Euler seems to assume something along the lines of what this principle says. I don't have any specific comments to make on sections 117 and 118. In section 119, Euler uses the phrase denotante che, where the word denotante is the ablative singular of the present active participle denotans, denoting. Euler appears to be indicating by this that he is using the symbol k to denote something, and by using the ablative case of the word denotans, is able to indicate the case of the presumably indeclinable noun k, in a similar way to which ipsius is used in the phrase ipsius zeta to indicate that the indeclinable noun zeta is understood to be in the genitive case, which I pointed out in the first video. Euler's deriving infinite series representations of exponential and logarithmic functions in section 119. As you may have noticed, he's giving very little consideration to the values for which these series are valid. And this is an important point to note because it's going to have some certain consequences, which I'll talk about more later in the video. In section 120, what Euler means by the final line of this section becomes quite clear when we attempt to evaluate the sum 9 over 1 minus 9 squared over 2 plus 9 cubed over 3 plus and so on, where it very quickly becomes clear that successive partial sums of this series oscillate very wildly between positive and negative of increasing size and, presumably, would never appear to settle down. The series that Euler has derived is being used outside of its range of validity, and this was not uncommon in Euler's time, and indeed Euler himself has no objections to using divergent infinite series. If a equals 10, then x equals 9, which is not in the range of validity of the series derived. Only values in the range -1 less than x less than 1 are guaranteed to work. And at the risk of repeating what I've already said in a previous video, here's a quote from Klein. Euler declared whenever an infinite series is obtained as the development of some closed expression, it may be used in mathematical operations as the equivalent of that expression, even for values of the variable for which the series diverges. Thus, he said, we can preserve the utility of the divergent series and defend their use from all objections. And we also read in Klein, as Newton, Leibniz, the several Bernoullis, Euler, D'Alembert, Lagrange and other 18th century men struggled with the strange problem of infinite series and employed them in analysis, they perpetrated all sorts of blunders, made false proofs, and drew incorrect conclusions. They even gave arguments that now, with hindsight, we are obliged to call ludicrous. Further remarks about the attitudes towards infinite series, and in particular divergent series, can be found in Klein's book. I'll also have more to say about this when we come to section 123. In section 121 we see Euler deriving a different series from which the value of k can be determined. This series, unlike in the previous section, is used by Euler with a suitable value. The series, as far as I can see, is again valid for -1 less than x less than 1, and in this case choosing a equals 10 gives x equals 9 over 11, which is less than 1. And so in this case, x is in the range of validity of the series, which explains why the approach of section 121 works, whereas the approach of section 120 does not. Euler introduces the notions of natural or hyperbolic logarithms, which are logarithms with base equal to the number 2.71828182845904523 and so on. This famous number is found by setting k and z both equal to 1 in the series for a to the power of z found in section 116. Euler uses the symbol e to represent this number, and thus e will denote the base of the natural or hyperbolic logarithms. Moreover, e equals 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 and so on. In section 123, when Euler speaks of finding the values of logarithms, he's saying that the series can be used effectively to find the decimal representation of logarithms to any desired degree of accuracy, and that these can then be used in turn to find logarithms of other numbers, using the properties already established of logarithms in general. It may seem unusual to calculate the values of the logarithms of fractions first, and then use these to calculate the logarithms of integers. But I agree with this approach, but for reasons which I think would probably differ from Euler's reasons, and I'll try to explain my thoughts, which are of course not definitive. Modern mathematics would recognise that the infinite series for the logarithm of 1 plus x, which Euler derives, is only valid for values of x less than unity, and for the time being let's just stick with positive values of x. Meaning the series converges to the true value of the logarithm of 1 plus x for values of x less than unity, or to use a more modern concept, within the radius of convergence. But the series does not at all converge to the true value of the logarithm of 1 plus x for values of x greater than unity, outside the radius of convergence. Thus, modern mathematics would acknowledge that trying to calculate, say, the logarithm of 3 directly from the infinite series for the logarithm of 1 plus x by using the value x equals 2 is an impossibility. There's no point in even trying. However, we can use values of x less than unity to find certain logarithms, such as those of 3/2 and 4/3, using x equals a half and x equals a third respectively, and then combine these logarithms carefully using the properties of logarithms already obtained to find the value of the logarithm of 3 in exactly the way that Euler does. That is, we take a more indirect method. The main point is that modern mathematics understands, at least well enough, the limitations regarding convergence of the series. However, as we've already seen from one of the quotes from Klein's book, which I gave earlier in this video, Euler was quite happy to write that -1 equals 1 plus 2 plus 4 plus 8 plus and so on. In other words, even though it would be quite obvious that adding any finite number of terms on to the right-hand side of the equality symbol will give a positive number, Euler seemed happy to believe that the sum of all of the terms would nevertheless still turn out to be -1. Rather than realizing that something was wrong with the logic here, he came to the conclusion, as we saw, that -1 must therefore be greater than infinity. This conclusion would clearly be rejected now using the more modern notion of limit and of course the understanding that -1 is not in fact greater than infinity. The point is that even though a series may appear to diverge, or in other cases oscillate wildly, Euler still seems to be convinced that the sum of all infinite terms of the series will still be equal to -1. And we've also seen in section 120 Euler claim that 2.30258 is equal to 9/1 minus 9 squared over 2 plus 9 cubed over 3 and so on. In other words, even though the partial sums of the series oscillate with increasing and unbounded magnitude, Euler asserts that the sum of all infinite terms will still end up being the finite value 2.30258. This equality is of course bogus. In section 123, Euler is suggesting using infinite series to calculate values of logarithms. Now, if we substitute x equals 2 into the series in the hope of calculating the value of logarithm of 3, then we'll find that as we add more terms to the series, the sequence of numbers that we get, the partial sums, will oscillate very rapidly between positive and negative and with unbounded magnitude. Euler, I imagine, noticed this but nevertheless probably believed that the sum of all infinite terms would still be equal to the true value of the logarithm of 3. It's just that to him, the convergence is very slow and not practical for calculations. And this is of course wrong. The series for the logarithm of 1 plus x is not valid when x equals 2 in the sense that the series will not converge to the true value of the logarithm of 3 at all. Of course, the modern notion of convergence didn't exist in Euler's time. Convergence would have meant a very different thing to Euler. However, Euler has realized that when small values of x are used, and presumably smaller than unity, then the series converges quite rapidly. Therefore, in order to calculate the values of certain logarithms as quickly as possible, it would be better in some cases to take the indirect method of calculating values of logarithms not much greater than unity, and then combine these carefully to find the logarithms of integers, rather than take the direct method to find, say, the logarithm of 3, since evidently in Euler's thinking, the convergence is much slower if we try to take the direct method of finding the logarithm of 3. Euler is therefore suggesting that the logarithms of these numbers, not much greater than unity, be calculated first for essentially practical reasons, that is, it's just quicker. The reason that the series appears to converge more rapidly for values of x less than unity and appears to converge very slowly for values of x greater than unity is because the series does not converge at all for values of x greater than unity, and for values of x less than unity, we're within the radius of convergence of the series. Therefore, I think that a modern mathematician would agree with Euler that it would be better to use the series to calculate logarithms of values not much greater than unity first, and then use these logarithms to calculate the values of the logarithms of integers, as Euler demonstrates. But the reasons given for doing this would be entirely different. Euler seems to have merely considered the convergence to be slower for larger values of x, and therefore impractical for calculation. A modern mathematician would acknowledge the complete lack of convergence for larger values of x, and thus the futility of trying to calculate anything meaningful using the series for larger values of x. In section 124, Euler explains how to determine common logarithms, that is logarithms to the base 10, from knowledge of hyperbolic logarithms, that is to base e. And finally, in section 125, Euler shows how the values of a to the power of y can be calculated. The logarithms in the series are hyperbolic logarithms, and the ay which appears in the text, or what looks like ay, should, I think, be a to the power of y. So that brings us to the end of this particular video. There was a lot to get through, and I'm certain that I haven't covered everything that I could have done. Nevertheless, I'll leave it there. I don't plan to make any further videos for this series for some time, as I want to move on to some other works. And there's only so much time I can spend looking at this work before I start to get distracted by other things. But I do hope to continue with this series at some point in the future. Please do remember to subscribe to my channel and hit the like button to show your support. Thank you for making it to the end of this video, and if you made it this far, I hope you found something useful amongst my remarks. If you have any ideas for future videos, things that you'd like me to cover, then please let me know by either sending me an email or leaving a comment in the comments section. Thank you for watching, and I'll look forward to making the next video for all my millions of adoring fans.